Hello. Hi. My name is Jordan. I'm a software engineer at Collabora, and I'm going to talk about kind of the similar subject to what was talked about previously, which is adding LiveKit support for the GStreamer WebRTC elements. So, yes, I've been working at Collabora since 2022. Previously, I worked at Amazon Video, and before that, much smaller companies. And yeah, I'm based currently in Fort Collins, Colorado, in the USA, and I'm originally from Los Angeles area. Yep. So what we're going to talk about now is basically what these elements are, which we can go through pretty quickly because probably most of us already heard this. After that, we'll talk about what LiveKit actually is, and then how we've implemented the bare minimum, which is the source and the sync element, and then a couple of extra features that we've added on. And then after that, we'll talk about what was the challenges faced. So what are these things? As we talked about before, they're the source and the sync. They're single-purpose elements. One can only send out, one can only receive. The nice thing is a lot of the annoying work is done, so you can actually get something going, just GST launched. You can evaluate it pretty quickly, whether you want to use it or not. And there's a bunch of implementations for various WebRTC systems. So what is LiveKit Server? It's a kind of like all-in-one system for doing WebRTC communications. It specifically acts as a selective forwarding unit, as you've heard before, which is kind of not exactly the peer-to-peer you've seen in like the most basic form of WebRTC. It gets between the peers, it gets between the members of a room, and it forwards data between them. So this kind of gives you a little bit of flexibility, and it allows more things to happen, basically. And one of the things it does is actually it prevents basically everyone from connecting to everyone as the chat room gets bigger. So that's one of the little things that it does. Some good thing about LiveKit is that it has client libraries for like many platforms. One of them is a Rust library. So we were able to take part of that and integrate it with the GStreamer Rust plugins. So this is what you have in the typical peer-to-peer situation, which is not what you have in LiveKit, where all the users talk to all the users, basically, depending on who they want to talk to. But within the selective forwarding unit, you basically have each user talks to the server, and they get the streams that they're supposed to get based on their preferences and that kind of stuff. So what do you have to do basic audio and video support? So as mentioned before, Olivier at Collabora implemented the first sync element for LiveKit, and this basically all you have to do is create a G object that implements the signalable interface, and have that forward all of it to work to the LiveKit client library. So basically create the offer after you do what's called ICE, which I don't know if you're familiar with that. Basically figures out how to create a connection between two hosts, which in this case is always the LiveKit server and whichever client is trying to connect. So basically those two things are what needs to happen in order to do the basic of setting up WebRTC connection. Everything else is actually handled inside the existing WebRTC source base class, or sync base class. So you really don't have to do much other than that. So what does a source do? It's very similar, just the opposite. So instead of creating the offer, you answer an offer from the server. And there's a different mode called consumer mode rather than producer mode. So yeah, it's like a lot of the same, but yeah, but it's just in the other direction. So one slight difference with LiveKit is, since it's a selective forwarding unit, it can give you all the people in the room, all their streams. So the default implementation that exists in GStreamer, you basically typically listen to one user. You have to put their name in their ID in the parameters, and then it'll listen to them. With this, by default, it'll subscribe to everyone in the room, so you can get like 5 or 10 audio video streams depending on who's in the room, and more will pop up as they join. So you can. Additionally, there's some controls that we've added to this, so you can put a filter, or you can keep the existing thing and subscribe to only one person. Yeah, so that's the basics of how the source works. On top of that, there's a couple other features we added. One of them is video simulcast. What this is it's kind of an adaptive technique where basically the sender, basically the sync element, can accept multiple streams of different qualities. Typically, it's like full size, then a quarter size, and a half size. And the quarter size and the half size they're like somewhere about like 30% or so in bandwidth of what the full size is. There's a lot of documentation on the LiveKit site about this. So if you ever want to look at that, they provide some interesting materials. So what happens is the LiveKit server, it decides for each client that's receiving these streams which one is the best one for them to get, based on the connection quality and the preferences of each client. So they can receive the big one, the small one, or the medium one, depending on conditions. So the ultimate thing that this does is any one bad client can't ruin the connection quality of all the other clients. So yeah, that's basically what it does. How do you do this with the GStreamer Rust plugins is actually kind of hard, because the design wasn't really meant to do all this stuff. So we have to make a fair amount of changes. There's a lot, but the basic idea is you have to provide the ability to group streams and then assign a role to each stream to rank them. Say which one is the best one, which one's the worst one. Once you do that, now you have to actually annotate the data streams coming out of the WebRTC sync. So this is all done with existing standards. So there's some RFCs for simulcast. Basically, there's a property called the MID, which basically defines a logical track for this purpose. And then within each MID, there's a set of RIDs that assign the rank, or and this is primarily by convention, at least the ranks. So it's like F will mean full size, H will mean half size, and Q will mean quarter size. I believe that might be in the standard, but I could be wrong about that. So currently the existing implementation doesn't have the ability to do any of that, although the WebRTC bin itself does. So we just have to kind of add the wiring between the two. Yeah. Let's see. So this is the kind of idea what this can do. So the sender sends multiple qualities, and the receivers can receive whichever one is appropriate for them, and that can change over time. So client A can get a bad connection, and they can go down to the low quality or something. Other feature added for LiveKit is end-to-end encryption. So one question you might have is, why would you even want to do this? And the answer is because you might not always be able to trust the LiveKit server if you don't control it. What happens with WebRTC is, if you know about it, the communications are encrypted, but the key exchange is not really under your control as a user. So the answer to that is, put another layer on top of it that you can control. So LiveKit offers this, and the most common way it's done is using a pre-shared key. And and basically from the pre-shared key, which is typically a password in the easiest case, you derive some keys. It's like let's see if I have a diagram of that. Let's see. Yeah. So basically, you derive an encryption key, kind of like a main key from password, And then from that main key, you derive actually a ring of subkeys that do the actual encryption. It's kind of interesting what they've done there. Let's see. Where were we? Yeah. So basically, if you don't trust the server, you switch to use end-to-end encryption. So what is actually LiveKit done here? They have this concept in WebRTC called insertable streams, which allows you to put filters either in front of the sender or after the receiver. So you can apply a filter, which is, in this case, a cryptographic filter, either an encryptor or a decryptor. And in order to make everything work, they've added their own kind of like data layout of every frame that comes through, or every buffer that comes through. The beginning is unencrypted of a certain amount, and then the end is encrypted, and then there's a little bit at the end after the encrypted part that includes like things, basically metadata for the cipher. They end up using AES GCM, which is of a kind of like a newer class of ciphers, which is called AEAD ciphers, which actually verify the unencrypted part. So it's kind of interesting that they do that. So yeah, basically here's the layout of an individual frame that comes through as encrypted based on their scheme. So the beginning is clear text. The rest of the media section is encrypted. After that, they include this AEAD tag, which is something used to verify. It's basically like a checksum that verifies that this entire the entire message is encrypted. Yeah, and then obviously the typical things you have in any AES thing is you're going to have an initialization vector, and then the rest of the buffer includes how long the IV is, and then which of those keys in the key ring is being used to encrypt this message. Yeah, so as I said earlier, they use a pre-shared key that's derived from a password. It's actually more flexible than that, but this is the most common case. And then from that key, you generate that ring. So this is what it does. So how is it done in GStreamer? You have to implement your own filters. Basically, the filters are, the way I implemented them, they just use OpenSSL to do the encryption because it has those ciphers built into it. The next thing is what happens when you payload them, and also how the layout is. The layout actually is codec dependent, which is unfortunate, but that's how they've done it. So for Opus and VP8, it's actually fixed. So Opus has like a couple bytes. VP8, if it's a keyframe, it's some amount. If it's not a keyframe, it's another amount. H.264 is most complicated case. In this case, you have to actually look at basically the bit stream. Everything before the first picture slice is unencrypted. Everything after that is encrypted. In addition to that, there is an escaping mechanism in the H.264 layout. You have to engage that because when you encrypt it, you could end up basically creating more of those stop patterns, and you're just going to mess up the whole thing. So you have to basically wrap it up in an escaping mechanism. So what are the challenges here? Primarily, there's a lot of specifications you're dealing with, so there's a lot of things mixing up. And you have to kind of find something that'll work in several different cases. Also, there is not much documentation on what WebRTC bin supports, so you have to just try and look at the code and see what is implemented. The next thing we kind of talked about before is we have to add all the grouping mechanisms in the WebRTC sync to support lining up all the streams and basically arranging them. Similarly, there was briefly discussed earlier about RTP header extensions. The changes that I've implemented, they actually add more header extensions, and they have to make sure that they don't conflict with other ones and that kind of stuff. So those are kind of the hard parts dealt with here. For the end-to-end encryption part, there's even more stuff. So talked previously about how it's codec dependent. So that ends up, manifesting in several different ways. One of them is I talked about the escaping part. You need to repack the H.264 streams if you're going to encrypt them, because you can confuse them. The next thing is GStreamer's RTP payloaders. Actually, some of them look into the data, and if that data is encrypted, then you can't really make sense out of it. So how do you get around that? There's a couple ways. One way is you can just include the original buffer in there, or you can just create some metadata, and then we'll have to modify the payloader to prioritize that metadata over what's in the actual buffer. Another thing I found is with H.264, the payloader actually trims off any trailing zeros. Why that's a problem is if you look back at this diagram here, this key number can be 0. So that's not good. So I had to add some little checks in there to fix that problem. Basically, if there's allow maybe 1 0 at the end of it. And now probably the worst problem is LibWebRTC interoperability. So this is mainly a problem with H.264. What happens is if you ever looked at the libWebRTC code, it has some interesting part of it that actually modifies the SPS unit that passes into it before passing it to the insertable streams. And that's also bad because it modifies the stream before the decryptor gets to it, which makes it fail makes it fail the verification step. So basically not the message that the sender actually sent. It does this on both ends. Most likely it is because they want to normalize all the parameters. That's my guess. And let's see. The way to get around this is you have to implement your own GStreamer element that does the same thing. Basically, before sending H.264 stream out, you have to actually basically fill in the defaults. So you have to parse the bit stream, fix it up the same way that libWebRTC would, and then they'll be able to handle it. So, yep, that's what I had to do to get all that working. And yep, and here's the development status. So the sync and the source were the first thing to be merged. The rest of it isn't really merged yet. So I have a draft out for the simulcast. It needs a couple changes. I think some of them are significant. And the E2EE, that'll come out next. Let's see. Aside from that, I can do a couple short demos of both. I think they're all running at the same time. So yeah. Any questions before that, or I'm out of time? Oh, okay. All right. Yeah. So I guess we can do a demo. We can switch to the other part. Thanks. Can you switch to the web browser, actually? There should be a web browser open. Yeah. Okay, so what we have here is a bunch of different things going on. We have a simulcast. We have 2 simulcasts and an encrypted stream. So these 2 simulcasts are not encrypted just as a matter of, that's just what I did because we want to get this demo working quick. Basically, as you can see, it says half size. If we let this go for a little while, it'll probably go to full. Yeah. So that's a simulcast. Same thing here. Make this one bigger. It'll go to full, and that one will go to half. You can even get it down to quarter if you try hard. The other interesting part is this one has that lock on it. So this one is an encrypted stream that I'm decrypting over the web. I can show you that it's actually encrypted if I just get myself out of here. This one is an encrypted stream, so I have this. They have a website that does a demo, but basically this is the password. This one has no password in it, so it should be broken. No password at the end. And let's see. So these unencrypted streams are working. This one's broken. It's never going to initialize because we don't have a password for it. Yeah, that's pretty much the demo. It's pretty quick. Any questions before we go? So I think I'm almost out of time. Yep. It does, you do, yeah. So that's part of it. I kind of excluded it because it's kind of, yeah, you still need it. Well, you might need it. Yeah.